This is example 312 in your textbook on page 103. This refers back to example 3.9 for the description. Essentially, this was the problem with the storm drainage of a community being a normal random variate, and they wanted to find a couple of things. The first one was the probability that the flooding or the flow would be greater than 1.5 mgd. So that was modeled. 3.9 was modeled as a normal random variate. Now example 312 asks us to use the same data and the same questions, but to model it as a log normal random variable. Since we were given the parameters of the normal distribution as the standard deviation, so 3.9, the data was the mean was 1.2 and the standard deviation was 0.4. In order to transform this into a log normal distribution, we need to find the parameters zeta and lambda. And I've rewritten the equations here for what zeta and lambda are in terms of our normal distribution with mean mu and standard deviation sigma. So we just simply plug and chug. So zeta squared is going to be equal to the natural log of 1 plus this coefficient of variation squared, which is the standard deviation, 0.4, divided by the mean of 1.2. We square that, and we end up with the natural log of 1 and change, which is equal to 0.105 for zeta squared. Therefore, zeta is the square root of that is 0.324. In lambda, we use this relation. Lambda is the natural log of the mean, which is 1.2, minus 1/2 zeta squared, which was 0.105, and this gives us a lambda of 0.13. So now the probability that x is greater than 1.5 is equal to 1 minus the probability that x is less than 1.5. And this becomes 1 minus the CDF function of, now using the log normal. Before we did the normal, so we had simply the CDF function of the mean of x minus the mean divided by the standard deviation, but now we're forming this into a log normal, so we need to use the definition given before of s, which is the natural log of x minus lambda divided by zeta. So we say the natural log of 1.5, that's our x, minus 0.13, that is our lambda, and we divide that by the standard zeta parameter, which is 0.324, and this gives us 1 minus the CDF function of 0.85, and when we use our tables, we find that that is 1 minus 0.8023 rather, and this all comes down to 0.198. For part B, we want to know what the probability of the drainage will be between 1 and 1.6. So previously we had the normal distribution. Now with the log normal, it would be slightly different. So we want to know what the probability is that x will be greater than 1 but less than 1.6. So this is going to be equal to the CDF function of, again, natural log, where you need to use the S definition here because we're in a log normal distribution. Natural log of 1.6 minus 0.13 divided by 0.324 minus the CDF function of the natural log of 1 minus 0.130 divided by 0.324. And when we crank this out, we see that we get 0.509. And finally, the 90% value of drainage from the community with a log normal distribution. So part C, the 90%, so we want to know the probability that x is less than or equal to the 90th percentile. Okay, and this was similar to before, except now with the log normal distribution, we have the CDF function of the natural log of this value, whatever it is, so we're trying to find, minus 0.13 divided by 0.324, and this has to be equal to our 90%. So when we take the inverse CDF function of both of these, we end up with the natural log of x at 90th percentile minus 0.13 over 0.324 is equal to the inverse CDF function of 0.90. And when we solve for the parameter x, 0.9 is going to be equal to the exponential function, or e raised to 0.545, which gives us 1.72.